beta error rate in case of PAM or MPAM, we derived something, and today we'll continue with PSK. So suppose we have MPSK. M is a big number. Fine. And suppose that assume that these are so okay. This is there. So now okay. Right? This makes sense, or not? This is this is MPSK, right? So one thing that we notice is that the probability of error or the constellation is symmetric. Therefore, for equal prior probabilities, the of error in any symbol, so let's say this is S1. Right? Agreed?
Yes, sir.
Yes. So if we can error in this one, right? So now fine. Agreed?
Yes, sir.
Therefore, So we can write this.
So shouldn't that be J and eta I?
Oh, wait a second. R plus JQ. Sorry, I plus JQ.
Yes, sir.
Okay. So in phase and quadrature. I'm more comfortable with that. That's why I wanted to write I here, but naturally it came out as Q. So let's follow I and Q here. Fine. So this now basically what we have is that and I will write this. Right. So, but the problem is that we are looking at this constellation in polar coordinates, and this PDF we have in the form of Cartesian coordinates, right?
Yes, sir.
Yes.
So, in order to better characterize this problem, the PDF or the received signal in polar coordinates. Fine. So let R equal Ri plus JRQ equal B e to the power j theta. I can do this. V equals root over Ri square plus RQ square. Theta equals tan inverse RQ by Ri. Right?
Sir,
Yep.
the array is basically the NR plus root yes, right?
Where is NR? That is eta. Yes.
Okay.
Fine. So now what do we do?
Sir,
Yep.
sir, like here the domain, like each region will be defined by theta only, right? Like it doesn't matter, the magnitude doesn't matter right here, like for each.
The magnitude will show eventually will matter, but the decision regions are based on theta. You are right.
So here also, like if it is, if we are finding error, means error will occur only, like it will dependent on theta, right? Then, like
So the error, if you say this, so I suppose I draw a circle here. Fine, I draw a circle and I draw this circle, and I drop my pen arbitrarily on the radius of the circle. Say I want to drop my pen at an angle theta and I drop it, aiming at angle theta. So where do you believe that there are three circles, three things that look like circles, actually, not three circles, rather four circles, four ellipses. Sorry, because I don't have space. I have, so consider the inner three circles, don't consider the ellipse. So if I drop my pen arbitrarily in each of these circles, which of these circles will have a probability of getting a more accurate version of theta?
So I'm not getting your point. Like theta, like each circle will have only one point corresponding to that theta, right? Like
No. So what I want to say is that I want to guess the location of theta. Right?
Sir, the
Okay, so I want to say I'm throwing a dart. Easier version.
okay.
I'm throwing a dart, and the dartboard has these boxes.
Yeah.
So let's reformulate this problem, or look at this problem again, that I'm throwing darts and the dartboard is like this. So this starts, yeah. So this is like the sun. So now there are multiple concentric circles. So suppose there is I draw another circle over here. Fine. So now I want that I've divided this dartboard into regions based on the angles. Fine.
Yes, sir. Yeah.
Yeah. So now I want to throw a dart and want that the dart lands within that angle. Say it lands within this angle or this angle. Now, if I throw the dart from a distance, what will be the probability of the dart landing in with the same level of skill? The dart thrower has a given level of skill. So with the given level of skill, will the probability of the dart landing in the correct sector depend on the radius of the circle?
Yeah. Like if smaller circle, it is difficult to throw, whereas like if the radius is
smaller
large,
circle, it's difficult to throw. Larger circle, you'll have more leg room.
Yeah.
yes, sir.
So yeah.
Okay. Yeah.
So makes sense now?
Yes, sir. Yeah. Fine.
Yeah, great. So theta is this now. So how do we? So we want this FR to change into FR, but with V and theta. So do you remember? So probability random process. Did you do this thing? That if f of xy is known and then how to get f of do you remember, do you know this or not? Because I don't think this was covered in your probability and random processes course, and we didn't touch upon this in the previous semester. So
Sir, no, sir.
Division by its derivative, right? I mean, sorry.
yes,
Yes,
that is
yes,
for one
sir.
variable.
Jacobian.
Z and-
Variables.
I mean,
Jacobian,
so
yes.
So here Z and W are.
Z and W are, and so I have x and y. and I define ZW as a function or as a combination of functions of x and y. G is a vector valued function, you can say.
Okay, sir.
Okay, G1, GZ and GW, you can define it as a function. So then what we get is f of ZW is summation over I 1 upon J right? Now, yeah, J is the determinant of this thing. Therefore, or since we want everything in terms of W, we can conveniently flip things and nicely enough 1 upon J equals, since del y by del x equals 1 over del x by del y, we can do this, and what we get is x equal to z cos w, y equals z sin w. So del x by del z is cos w. Why do it this way? Let's why complicate things when we have a simple result? So del z by del x is nothing but 1 upon so x square plus y square, and this is 2x, yeah, 2x upon root over plus y square. This is so what is the derivative of tan inverse 1 upon tan inverse y upon x? What is this? Can anyone help me with this? It is
Upon a square plus x square. I don't remember
a square
correctly.
right?
Yeah, I guess. Yeah.
So the Jacobian term becomes 2x upon root over x square plus y square. This is for 1 over x square plus y square times so y by x. So 1 upon x square plus y square x square, sorry, y square upon this, and here it is 2y.
So tan inverse x by का derivative is a upon a square plus x square. I just checked.
A upon, okay, so
Yeah, x by
that
a.
makes life,
Yeah.
that makes life a lot simpler. This, so this becomes, there should be a minus here for this to be consistent. Either of these two terms should have a minus. This. Yes, so minus will be there because here, so this is y by x. So because of x being in the denominator, this will have a minus. D by dx tan inverse y by x will be minus y by x square plus y square. Yes. And this 2 will cancel out because there's a half there. Yeah. So this. Fine. Check for any other class 11 or class 12 derivative errors. Fine. Because I have the final result written in my notes, not the steps. This is the final
Yes,
result. Yeah, so this I will write again. X divided by root over x square plus y square, y divided by root over x square plus y square, minus y by x square plus y square, and x divided by x square plus y square. Now this equals x square plus y square divided by x square plus y square raised to power 3 by 2 equals 1 upon x square plus y square equals 1 upon z. So 1 upon j equals z. Fine. Consequently, fxy or fzw thankfully for each xy there will be just one zw, right? So the so you know that Cartesian to polar mapping is unique or invertible?
Yes, sir.
So since Cartesian to polar mapping is invertible, this summation will contain just one term. So we are saved over there. We just have one term and we put it here. So z in the numerator times fxy I can write as 1 upon pi n naught power z square cos square w plus z square sine square w plus mu square minus 2 mu z cos theta divided by n naught, and there's a minus sign here. So therefore f theta or f v theta given s equals so z square cos square w plus z square sine square w turns to z square, that is v square plus e minus 2ev cos theta right?
Sir,
Yeah,
2 root e v cos theta, right?
yeah, 2 root e. Sorry. Yes. Fine.
So what is the step we actually did here? Like what we were trying to do in the above steps, like to reach this?
So what we have done is we have reduced we have moved from the Cartesian coordinates to the polar coordinates.
Okay, writing the function in terms of polar coordinates.
Yes, we have written the function in terms of polar coordinates.
Okay, sir, fine.
Now you can say that this one is when theta mod theta right.
Yes, sir.
So therefore step 1, so the first thing is that we have to, so this is the probability of error is independent of R, or the probability of error doesn't contain an R term, or the error event doesn't contain an R term, which means that we have to obtain theta given S1 equals F right. Kirti, does this answer your question further?
Yes, sir, fine. Yeah.
So this beast. So if we look at this beast, what we get is that this equals T V, sorry, 1 upon pi n naught outside minus v square minus 2 root e v cos theta times fine.
Yes, sir.
So And yes, this times v, because there's a v sitting here as well. There's a v sitting here as well. So this thing.
So it's plus 2 root e v cos theta, right? It should be.
Yeah.
Like
It's minus.
Like if you, bracket, yeah.
So the minus sign was outside this fraction. So when I write minus x plus y, so this minus is generally considered outside, but yes, there should be a bracket. Fine. And the probability of error, or PE, one minus fine, this beast. So the problem with this approach is that we need to calculate this numerically, because you can see that we cannot have a closed form of these two integrals. So this becomes a double integral. The first one I can still look at the table of integrals and try to evaluate, but the second one, or this integral, since it has fixed limits, I can still try to evaluate it from the table of integrals. But this one, the lower one, we have to evaluate it numerically. So the exact probability of error can be obtained if needed, but there is no closed form expression. Fine. We cannot write it nicely as a closed form expression. So now you feel slightly more motivated to use the union bound, I believe, after all this effort.
So then union bound is basically easy way out.
Yes, so we use the union bound. So this is a MPSK is a simple constellation. Right? Isn't MPSK a simple constellation? MPM we did yesterday. MPSK is a simple constellation, and we tried to find the bit error rate and with the symbol error rate, and we say that we can find the symbol error rate, just that if we want to design a system numerically, if we have enough computation power, see, this integration doesn't require much computational power. You have done all those numerical techniques, Simpson's rule, etc. Simpson's rule. Simpson's rule is the trapezoidal rule, Simpson's rule. You have done these things somewhere in math.
So trapezoidal, we have used it recently.
Okay, where?
Sir, in microelectronics lab.
Oh, you have used it in microelectronics lab. You haven't had a course on numerical methods.
No, sir.
No, sir.
Okay, you don't know how to solve using Newton's method, or how to solve strange looking equations using Newton's method, and
So we know Newton's method.
numerical differentiation, etc.
So we know Newton's method.
We know techniques, but they have been taught scatteredly in different
Yeah,
labs.
exactly. Like it's more like self-study rather than a correct
Okay,
course.
so there's a thing called the, well, there's there's a method called the Runge Kutta method that looks offensive when you write it. That's why I'm not writing it. That can be used for solving differential equations. So maybe if you need these, you can look these up, but those are interesting techniques. So numerical integration, possibly Simpson's rule, can be used for calculating this, and this is not Homer Simpson or Bart Simpson. Anyway, so this, and there is another approach, the approximate method. For so what we did was the exact way, then the approximation, and then the union bound. So again, I draw the MPSK constellation. This time I draw these points slightly more far apart. So you can see that the length of, so for large M, the separation between two points is effectively approximately right. Agreed?
Yes, sir.
Which can be approximated as fine.
Yes, sir.
And therefore and it can cross over into this, or it can cross over into this. These are the most likely outcomes.
Yes, sir.
So approximately equals SM plus 1 SM, right? This equals 2Q this beast. Fine. Sorry. So the probability of error is approximately equal to this, and the union bound this piece. Fine.
So,
Yeah.
so length of the arc is given by r theta, like which could be approximated as r sine theta, right?
Yeah.
Here the theta is 2 pi by m. So inside the sign, why we are writing pi by m instead of 2 pi by m? It doesn't matter.
So since pi by m is infinitesimally small, so is sine pi. So pi by m and 2 pi by m will both be infinitesimally small for large m.
Yeah.
And we get a nicer looking expression with the 2 outside.
Okay, fine. So it basically doesn't matter like inside or outside.
Yeah. So these are close enough, and these are approximations anyway.
Okay, so then.
Sir, for large M, I mean, is the noise variance small enough that we can say that most of the probability will be within the neighbors, the immediate
So
neighbors of
that
the.
see, no, you can transmit as large power as you want.
Okay, sir.
Okay, so see, that's why this 2es by n naught we have. So your lab sheet 5, I believe, has this experiment. Fine. So,
Sir,
yeah.
sir, except that the 2 is in the numerator, I am not finding a strong reason for the approximation from pi by m to sin pi by m.
That is the only reason.
Just to bring 2 to the numerator.
Yes. That is the only reason.
Okay.
You cannot say that except this, there is nothing, where that is the main reason. I can always say that, okay, yeah, so I went to the restaurant, but they didn't have anything except food. This is the main reason that because so taking 2 inside will still give you the a similar approximation, but it will be less elegant. This gives you a more elegant approximation. That's the only thing, or that's the only difference. Another thing can be that, okay, sine pi by m approximates pi by m better than sine 2 pi by m approximates 2 pi by m. That is always there. So this is an endless debate. Let's not invest too much time into this. So the next thing is, so we have done PM, we have done PSK. Now let us look into QM. So in general, for QM, R is a complex number, and so is Sn, right? And the decision regions and A. Now the question is that
Sir, you are not audible properly.
now I am audible. Now am I audible properly?
Yes, sir, yes. Now it's
Yes. So yeah. So R is a complex number, so is Sm, and the decision regions depend on the shape of the constellation. This is okay.
yes, sir.
So now the point is that if I say want to use 8QM, then what will you use? Is this 8QM?
Yes, sir.
So we were having something like in between, right? Like what?
Just a second, Kirti, just a second. So red pen come. Is this 8QM? The circles?
So what about the topmost and the lowermost?
No, I'm asking, is the constellation represented by the circles? So yeah, I should always label the axis. So is the constellation represented by the circles 8QM?
Yes.
Yes, sir.
So let's say triangles. Eight QM again? The constellation with the triangles?
Yes, sir.
So when I say 8QM, which of these will I use? That is the question. So how do we decide? So given.
So will we get the same answer? Like I don't know. Like
I will give the answer. The multiple choices for QM. How do we decide the constellation that actually want to use? So guesswork.
Sir, is it based on decision regions? Like the larger decision region will be chosen.
Larger decision region. What do you mean by larger decision region? There are multiple constellations. We want to choose one constellation out from which we will transmit.
So the triangle one.
How? Why? I can
Sir,
draw another one. I can draw one with squares that will have a different structure. Why would you choose the triangular one here?
so like my logic is that in the small circles one, it would be harder to exactly like the interior points, except the exterior points, the interior points have a less smaller regions where the
So
error
there
won't
are
be.
4 exterior points in all these constellations. You might see that as well. So all these 3 constellations have exactly 4 exterior points. Right?
Yes.
So the minimum distance is the maximum in the triangular one, right?
Because the constellation is larger. Or So you are close to the point, but not precisely on the point. So what we had defined was another term, the average energy. Equals summation I in S, or I equal to 1 to M for simplicity. Why complicate things? They are already too complicated. Let this be over M. We had defined this average energy, if you remember.
Yes, sir.
So since we had defined this average energy, now if I tell you that uh, so if I tell you that 3 constellations are making your life simple, if I tell you that, say, cross BER, so, or symbol error rate, probability of error, E average. I'll draw a table for you and tell you that say cross, triangle, circle, square. There are 4 constellations to choose from. Fine. So will this help you decide?
So it's a trade-off between the probability of error and energy.
No.
transfer.
So will this? So there is a multi-layered question actually. Will this table help you decide? No, this table cannot help you much. What you want is you want either of these 2 parameters to be constant. Like based on this table, I can say that both triangle and circle work for the work at probability of error 10 to the power minus 5. One consumes half a unit and the other one consumes 0.6 units. So obviously there it's a clear choice, but otherwise it's not a clear choice. Otherwise you are always comparing apples with oranges. Right?
Okay, sir.
So the first thing that we want to do is make either the energy constant or the probability of error constant. Say I force everything to, I'll redraw this table and I force everything. So because I can have closed form, I can have the union bound for different constellations, and I can have I can numerically calculate the probability of error for different constellations by some tricks. So cross, triangle, circle, square. The probability of error in each case I fixed to 10 to the power minus 5. And say 1. This is 1.2. This is 1.4. This is 0.9. Suppose this is true. So then is the answer easier?
Yes, sir.
Yeah. So you choose the constellation that minimizes your electricity bill. because see, you can always control the energy that you spend.
So, but how did you normalize it like this?
We can, you'll see. We can always scale down. So you always get the expression in terms of E average by N naught. You just say that the expression is always in terms of E average by N naught. You can always say that based on that expression, what is the E average that I need to get the probability of error for a given noise variance. Right? So the expressions
sir.
that we have derived are in terms of are in the form like this, that PE equals Q of some G or some K times root over E average by N naught. Till now, these are the kind of expressions that we have had. And this is a general form. Say C. This is the general form.
Yes, sir.
Right? So if this is a general form, then what I can do is that I can decide that I want some symbol error rate or probability of error and call that P naught, and using inversion or using this expression, I can calculate the required E average. So E average is always under my control. I can calculate the required E average. That is one approach. Another approach can be, I know my budget. That I cannot transmit more than, suppose I cannot transmit more than 1 joule per bit. I know my energy budget. Then what I will do is use these expressions or use the BER expressions. Calculate each or P for each constellation for the given energy budget, and so you can either keep the energy constant or you can keep the bit error rate constant. Fine. Say you want a phone that has a 48 megapixel camera and you don't worry about the budget. The first approach is like that. The second approach is that, okay, you have 10K and you want the best phone in that comes for that amount. You have 15K maybe. So uh, two separate approaches, but in both the cases, you want to maximize the energy efficiency of the system, because if you're spending something, you say that I want to spend this much, I want the best outcome, or I want this outcome and tell me how I want to spend the minimum for that. Fine.
Yes, sir.
Yes. So we choose constellations, QM constellations based on this, but thankfully, rectangular QM. Oh, Oh, it's past time already. I didn't notice.
Yes, the class has started. Can we
Oh,
stop?
sorry. Please continue. Oh, sorry. I'll stop here and we'll continue tomorrow. I didn't notice today.
Thank you,
Sorry.
Sam.
Thank you, sir.
Bye.